All right, guys, welcome back. So last week we covered chapter 3. We finished talking about chapter 3, and now we're going to jump into chapter 4, which we'll talk about gases. So I was just recording for like maybe half an hour, and I forgot to check the time, so I'm starting over. So yeah, please forgive me for that. But to recap, we want to make sure that we know that Tuesday is when chapter 3 homeworks will be due at 11 p.m. If you're a student who recently added last week, which last week was the deadline to add classes, we can work on again extension just so you're caught up. So if you're one of those students, please let me know. I granted extensions for chapter 2, and I could do so for chapter 3. But chapter 4 and onwards, everything's fair. Everything's going to be due for everyone. So you should be caught up by then. Chapter 4 homework will be due next Tuesday at 11 p.m. I think I'll get through chapter 4 by Thursday. I'm pretty sure. It's considerably shorter than chapter 3, so it shouldn't be too bad. And I won't try to load your brains with too much information. We'll go through this slow, and we'll see what we do. We'll see how we're doing at the end of this lecture, and whether or not I need to slow things down or maybe take things up a notch. All right. Okay, so chapter 4 is gases. So we kind of touched upon gases in chapter 1 when we're talking about states of matter, but now we're going to be talking about more properties of the gases and how they relate to chemistry. Okay, so the characteristics of a gas: gases may be compressed. So if you have a container of gas at a certain temperature and pressure, you can actually apply forces like a piston, for example, and push on the gas, and that will actually compress a gas. And once we compress the volume, we're actually we're going to affect the kinetic energy of the gases, and they'll be hitting the container walls with much more frequency, and that will drive up the kinetic energy, and that will increase the pressure of the gas. Gases can also be expanded. For example, if I have a balloon filled with gas, I can open the balloon, and the gases now will expand outward to the atmosphere, so they have a much bigger infinite volume to be scattered or occupied. So that's gas expansion. Gases tend to have low densities, and that's because the gases are so far apart, they have no attractive forces to other molecules of the same gas. So they don't tend to be very dense, as in where liquids and solids, they're close together, and they do form a very dense material. Water, it always, depending on what liquid you have, it can sink. When you have metallic objects like metals, like a metal bar, rod, nail, like iron nails, when you place them in a beaker of water, they will sink to the ground, sink to the bottom, because they're very dense. Solids are very dense, and they have very strong attractive forces that gives them definite shapes and sizes. Gases can be mixed in a fixed volume. So say I have a container with one gas that's closed off to the atmosphere, and then I have like a little entry port to inject another gas. I can actually add gas and have it mixed into a mixture, a homogeneous mixture. So gases, for the most part, are usually colorless. We can't see them. One gas we can't see is steam. Steam actually appears white, and that has to do with a property of steam and light. But we won't talk much about that. Also, the atmosphere around us, right, is a mixture of gas, oxygen. I think there's fluorine in there, nitrogen, Well, I'm not sure about fluorine gas, but I think fluorine is a gas though. It may be in the atmosphere. But I think a majority of the atmosphere is oxygen, nitrogen, um, hydrogen, also argon. So there are also some noble gases in there, but mostly it's nitrogen and oxygen that we breathe. So the atmosphere is a mixture of gases that we can. So the property gases we can mix and they can exist um, in a stable mixture. Of course, if you mix stuff like oxygen, hydrogen, that's a potentially dangerous mixture because if it has an ignition source, yeah, it can form an explosion. But that's usually like in a contained environment, not in the air, because in the air at any one point, the gases are not going to be colliding with each other because there's so much volume in the air, in the atmosphere above us, that virtually the collisions are not going to be a frequent event. And then that on that note, once we have a container of gas with a fixed volume, right? Gases will exert constant pressure on the walls uniformly in all directions. So a gas will be moving very fast and it'll move in all directions, colliding with the walls very rapidly. Okay, so gases will exert pressures, and that the pressure is dependent upon what kind of vessel it is in, what container, how big is the volume, and the temperature. And we'll get into those factors in a few slides. So okay, so we just went over that the pressure of a gas is caused by the gas hitting hitting the container walls. So that explains why our density of a gas is particularly low. For example, a balloon of gas, when you put in a beaker of water, it'll float to the top because the gas molecules are not dense or compact. They're very spread out in the balloon. So at any one point, the pressure or the main bulk of the gas particles is going to be expanding the balloon, right? Or sorry, not expanding, but hitting the surface of the balloon in all directions. And that's why the balloon looks so circular as it does, because if the gas were only hitting in one direction, you wouldn't expect it to be circular in shape. But since the gas is moving in all directions and exerting pressure on all sides of the balloon, that's why we get that definite shape that the gas occupies. Okay. So in here in the middle, I just drew some water molecules. They're tied together, but I drew some like speed lines between the water molecules because they're actually vibrating in solution. So water are actually vibrating. They have strong attractive forces, but they're not as strong as a solid. So water will be more dense because see how the molecules are kind of compact in the structure inside the beaker. They'll be dense. They'll be much more dense than a gas because the gases are moving around in all directions, no attractive forces whatsoever. But in our beaker here, the water molecules, they'll be somewhat compact and dense. In the case for a metal, the molecules of the metal, or in this case maybe the atoms of the metal or the particles of the metal, the individual units will be very tight together, like in this pile of circular shapes I drew. They're very close together, tightly packed, strong attractive forces, has a very definite shape, does not take the shape of the container. So it will be very strong and very dense, very concentrated, and that's why it sinks to the bottom of the water. And that's why it's the most dense of all three of them. Okay, So that is our density of a gas. They're typically the lowest, very low, compared to other states of matter. Okay. So now let's talk about the particulate level explanation of the characteristics of gas. So this is based on kinetic molecular theory that we covered in chapter 1 briefly. So gases consist of molecules in empty space right here. So what that means is that our volume occupied by the molecules is very insignificant or negligible compared to the size or the volume of the space they occupy. So for example, the volume of the container, we say the volume of the gas is very negligible compared to the volume of whatever space they occupy. So we say it's very small. In that case, on another note, when we talk about, gas is moving very fast and not occupying much space, that the fact that they can move around and they're not very, bunched together, they move independently of any other particle. We say that the attractive forces between the gas molecules are insignificant or negligible as well, because they're moving so fast, and they're not compact at all. So the particles are moving very fast at the temperature they're at. So that means the attractive forces are there's virtually none, because now they have enough energy to escape those attractive forces and overcome them. And the particles now are moving freely and are not influenced by the other molecules of the gas. So we say the attractive forces are negligible. And the average kinetic energy of the particles are only dependent or proportional to the temperature that we express in kelvins. So we talked about kelvins in the last chapter. We're going to be using them to refer to temperature in this chapter. So when molecules do interact with each other, since it's usually when we're talking about gases, we have them in an enclosed container. And when they're in a closed container, they're going to be in a very close environment. They're going to be very close to each other. And once they bounce off the walls, there is going to be some frequency of them colliding. And when we talk about them colliding with each other and the walls of the container, their collisions are elastic. So elastic mean that they collide, and after they collided, they still have the same kinetic energy. So their collisions do not result in loss of kinetic energy. So the speed at which they collide, they're going to keep moving at that speed after they collide. So that's what we mean by the interaction between the molecules have no net loss of total kinetic energy. So we may be revisiting this topic, but I don't think so, because the next time we talk about gases is chapter 14, and I'm not sure we'll get to that point in this quarter. But these characteristics that I just talked about are what you should think about when we're talking about gases. So don't think about anything else. There won't be any exceptions or anything. And if they are, I will tell you. But these are the characteristics we are going to be referring to when we talk about gases here. So, okay. So here's a picture of liquid water. Sorry if it's a very poor drawing. So this circle here is like a snapshot of the liquid water. So the liquid water, you expect the particles, if you were to see them, that they should occupy the space that you see. However, in steam, the particles are going to be moving really fast, right? Because at 100 degrees Celsius, that's when steam forms from water. And if you have all that steam there, it's going to be bouncing off the walls in the container if it's closed, like we have here. And what you see in like a snapshot, like at any particular moment, you're going to see many snapshots that are just empty space, because the gas molecules are moving so fast that it's impossible to maybe snapshot them in the camera. Of course, you can't really do this with a normal camera, right? This is just kind of like a concept question. Like if we have a snapshot, at one point you'll see at like after many snapshots, you'll see maybe a point where there is a gas molecule in the lens, but that's going to be very, very rare. Maybe after like 20 snapshots or 10 snapshots, you'll see maybe a gas molecule. Whereas in the liquid, after each snapshot, you'll just see the liquid because they're very close together and very like compact. The molecules are very close to each other, kind of compact because it's the liquid, right? The liquid will occupy a certain amount of space. Excuse me. So the liquid will only take up the space where the liquid is touching the container, right? It's not like the liquid can flow above the container unless you move it. It'll be contained within the liquid. So each time you take a snapshot, the molecules will be there for the liquid. Gases, you can't see the gas molecules, but the steam, it's going to be enveloping the whole container. So it'll be moving very fast within the container. And each time you try to look at that snapshot, the gas molecules are not compact. They're moving so fast. So you won't see the gas. So it'll mostly be empty space right here. Okay. So next, let's talk about pressure. So pressure is force per unit area. So force per unit area, what that means is, so pressure, we say it's force over area, or pressure equals F over A. So the pressure, what we mean about pressure is, so when we think about pressure, it's like that force of particles hitting a surface, right? Like water pressure, like the water pressure out of a faucet. You could increase the pressure by opening the faucet and increasing the flow of water. So it's the same thing here. It's the effect of the force of the interactions of the huge number of rapidly moving molecules of a gas. So it's moving back and forth within the container. And as they collide with a surface of an object that's in contact with the gas, that frequency of collisions, that gives you or the force of the collisions, that gives you the pressure reading, or that phenomenon we call that the pressure of the gas, or the pressure of the substance. It can also work for water pressure, but we're not talking about water pressure here. We're dealing with gases. Okay, so if we have those interactions of the gas particles hitting the surface of our object, what affects the pressure of the gas? Well, there's three things: volume, so the volume of your container. So we'll talk more about volume. We'll actually talk about how volume affects the pressure in a minute. So volume will affect this. So say you have a container with a large area for the gas to occupy, right? So that large area means the gas has more room to move. So it'll move at a certain speed. But now at that same temperature, if you decrease the volume like so, now the gas molecules now have the chance to collide. The frequency of collisions will actually increase because there's less space for the gas to occupy. And when they collide, we say that their kinetic energy is unchanged, right? But as they to maintain the same the same relationship between pressure and volume, to maintain that pressure and volume relationship here, if you decrease one variable, the other variable must move in the opposite direction if you're keeping things at constant temperature. So if we decrease the volume, the pressure will increase because the frequency of collisions between the walls and the molecules and the other molecules will actually increase. So those frequency of collisions will add to the kinetic energy, and that will increase the pressure, and the frequency of collisions will increase. So that's one way of looking at why pressure increases when you decrease volume. But we'll talk more about that soon. Also, amount of gas. So you have more gas particles. The pressure will be affected because you'll have more particles or molecules of gas hitting the surface of your of the container, so that will affect the pressure. Temperature. If you increase the temperature, you increase the average kinetic energy. So the speed of the gas molecules will increase, and the frequency that will hit the walls and other gas molecules will also increase because it's moving much faster. So those are factors that affect the pressure of a gas. So next, let's talk about how we measure pressure. Okay, so here's my very crude picture of a barometer. So the Mercury Barometer is like this. So in the slides, it's figure 4.7. There's a better picture, but I just represent it here as I talked about it. So what this is saying is, see in my little dish right here that says Hg mercury. Sorry if it's not very clear. I will highlight it in blue. So here's my Hg mercury. So mercury, actually, that liquid is called quicksilver, because I don't know if anyone's ever seen Terminator 2, but the bad guy who can like turn to liquid metal, that's liquid mercury. That's what liquid mercury looks like, and mercury looks like a liquid at room temperature. So it's very, 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 very toxic. We do not use mercury a lot in applications anymore. It's been phased out due to OSHA concerns. It's because it's very toxic to the brain. They use there's many years ago, there were reports where mercury poisoned fish and it was affecting them neurologically, and it would just kill the fish population. So mercury is something we do not work with at all anymore. Even in laboratories, we try to avoid mercury products, mercury reagents, mercury intermediates. However, mercury is still used in electrochemistry for electrodes, for as a standard electrode to record potentials for chemical species. So it still has some use. But nowadays we don't use it. Anyway, so this dish is filled with mercury. That's denoted in black. And my atmospheric pressure is this. I'm just going to overlay it blue here. This blue arrow. So what it's saying is that this tube right here, the mercury will be pushed into the tube by the atmospheric pressure, and that will balance the pressure between the mercury in the dish that's underneath the tube and the atmospheric pressure from the air in our environment. So here, atmospheric pressure is this value, 760 millimeters of mercury. We'll talk about other units, but that's the standard unit. Other units include 760 torr, 1 atmosphere, but we'll talk about that. So what this is saying is that the pressure at the bottom of the mercury in the tube, so the mercury at the bottom of the tube, is balanced by our atmospheric pressure. So it stays still, and we can record that reading, which is 760 millimeters. So to recap, the atmospheric pressure, PATM, or atmosphere, is equal to the pressure of the liquid mercury in the tube. So that's how we balance them out. And in the tube, the reason why the atmospheric pressure enters the tube, because once we submerge a tube within another liquid, the liquid won't automatically go into the tube, but there is a vacuum that kind of creates a pressure difference that allows the mercury to go up the tube, because in the vacuum there's no pressure, and areas of higher pressure will tend to go to areas of lower pressure. So it's kind of like pressure equilibrium when there's a pressure difference, but don't worry too much about that. So that's my schematic here for the Mercury Barometer, or how we measure pressure traditionally. Okay. So this is where we stopped, or where I got cut off and realized I wasn't recording the time. So the time we have now is, we have a little bit over 50 minutes. So let's talk about the properties of a gas. So the properties of a gas are such that, so here's my property, and here's my description here. And here's my relationship to gas pressure. Okay, let's go. So pressure, we're going to talk about pressure first. So let's just make a different color. Pressure. Let's denote that as P. So description is force over area, right? So the force of the gas hitting that unit of area. So there's no relationship because that's pressure. Volume now. Volume, or V. So what does volume do? So the volume is the quantity. So the quantity of three-dimensional space occupied by a gas sample. So what is this relationship? Well, pressure is, we say that pressure, so let's say P, so P is where pressure is proportional, inversely proportional to 1 over V, or 1 over the volume. So that's what I was talking about when I decrease my pressure, my volume must increase based on this relationship. And then if I decrease the volume, my pressure should increase, right? Because if I have 1, right, and 1 over volume of a very, very small number, then my the pressure should increase to remain proportional to that relationship. So if I have high pressure, low volume, high volume, low pressure. So inversely related, and that has to do with the frequency of collisions based on decreasing volume versus and increasing volume. Okay, so that was volume. All right, let's talk about amount. So amount now has to deal with the number of gas, molecules. So we won't actually have abbreviation yet. So the number of gas molecules in a sample. So our relationship is P is proportional to amount. So pressure is proportional to amount. That's deal with the collisions that we see for gas particles. For it has to deal with the more gas molecules or molecules that we see, that will give us more pressure because we have more collisions between the molecules themselves and between the molecules and the walls of the container. So amount is proportional to pressure. Lastly, we have let's choose like, I don't know, purple. So let's talk about temperature. So the temperature, here's the definition. It's the average kinetic energy of the gas molecules in a sample. So temperature, temperature around us, that's just the average kinetic energy of the gas molecules in the air. So when the temperature is very high, that means the gas molecules are moving very fast and the average kinetic energy is very high. So in this case, we'll call this T. Pressure is proportional to temperature. So as we increase the temperature, the average kinetic energy will increase, and that will increase the speed and the frequency at which it will hit the walls of the container and other gas molecules. So the collisions will increase, and that will result in an increase in pressure. Okay, so that is the properties of gas here. So make sure you kind of are familiar with each of them. All right, let's move on. Okay. All right, now we're going to talk about pressure units. Pressure units. Okay. So the two most common one is atmosphere. One of them is atmosphere, so ATM. So atmospheric pressure is referred to as 1 ATM. So it's unit. So this is a definition, not really important, but let's study the history of the unit. Unit of pressure based on atmospheric pressure at sea level. And capable of supporting a mercury column. (760 millimeter high). So that barometer we talked about, that is the definition of atmospheric pressure. So that's where 1 ATM comes into play. 1 ATM equals 760 millimeters of mercury. So at sea level, pressure does change below sea level. So at the ground or at sea level, the pressure is based on the atmospheric pressure in the air at sea level, and that is capable of supporting a mercury column at 760 millimeters high. So that barometer diagram we looked at, that is the definition of the ATM. Okay, let's use a different color. So now we're going to talk about torr. So that's the second most common unit that we use. There's actually torr, there's bar, there's a lot, Pascal. So it helps to know all of them because you may encounter them in scientific research, industry, corporations, if you're working for companies, stuff like that. Excuse me. Unit of pressure equal to 1 millimeter of mercury. So by definition, 1 ATM equals 760 millimeters of mercury, which in turn equals 760 torr. So 760 torr, 760 millimeters mercury, 1 ATM. Those are three equalities you should know. if I do give you pressure questions, I probably will not ask you to memorize the conversions, but know how to use it and convert to the appropriate unit. Okay, last one is Pascal. Oh, is this hard to read? I think it's okay on a yellow white background. So Pascal. Okay, so Pascal is actually the SI unit of pressure. So this one is the one that is recognized around the world. So SI unit of pressure, and it's equivalent to 1 Newton per square meter. Like so. One ATM equals 101/325 Pascal. So when we're talking about the SI system, like the prefixes, we use Pascal as our unit of pressure. So for example, so 101,325 pascals. Oops. And we can convert this to 101.325 kilo pascals. Sorry. Excuse me. Losing my voice. So kilopascals is just the another SI another metric unit for Pascal. So you can use either one of them. You might encounter both pascals, kilopascals. Sometimes there's megapascals if you're talking about really high pressures, for example, industry like hydrogenations. But don't worry too much about that. However, there's more. Lots of units. Bar. Let's talk about bar. Not the Attorney General. I probably shouldn't have mentioned that, but sorry, bad joke. Bar, as in like the pressure unit and maybe a bar of chocolate. So 1 bar equals, man, just watch this video get flagged. Kilopascals, or equals 100,000 pascals. So 1 bar. So bar is also a very common pressure unit for other applications. We won't worry about that. So 1 bar, 100 kilopascals or 100,000 pascals. So just let me go on the top here and just keep our units consistent here. I don't want to use a capital SK, that might confuse people. So let's use a lowercase k. All right. 100 pascals, 100,000 pascals, sorry. So now there's inches of mercury. So there's millimeters of mercury, inches of mercury. Inches of mercury is is less commonly seen, so I wouldn't worry too much about that. If I do give you a problem, I will definitely give you the conversion. I'm not too picky about this one because you rarely see it. So inches of mercury. Oops, wrong. How do I go back? Oh, sorry guys. Pick up there. Okay. Inches of mercury. So 1 ATM equals 29.92 inches of mercury. So it's very similar to millimeters of mercury, but you just convert that to inches. But this one is very, very, very rare. Very rarely encountered. So we won't talk too much about that. Last one is pounds per square inch. Pounds per square inch. So this is another common one. So you may have seen pounds per square inch in like your bike tires. So if you're in Davis, you probably got a bike to get around the campus and downtown Davis, which is usually at this time of year packed with undergrads. But it's probably not because of COVID, which is unfortunate. But you know, safety comes first. But anyway, you have a bike, usually in a bike, on bike tires, there's something called PSI, recommend PSI for air pressure for your tires. And usually that's something you should stick to. What that means is that's something called PSI. So that's another common one for like tires and, you know, like vehicles, stuff like that. So PSI is force of 1 pound. 1 pound applied to an area of 1 square inch. So the equation we want, or equality we want, is 1 ATM equals 14.70 PSI. So one thing you keep in mind is PSI is a common one for Pascal, torr, and atmosphere. So all of those are pretty common. I might test you on one of those. We do not, I don't know yet which one, but if you were to encounter a problem like this, I will give you the conversions. So do not worry about memorizing. Just be aware of how to use them in the calculation. Okay, so I think that's the end of our pressure units. Now, next, let's talk about how we measure pressure. So we talked about using the barometer, but now we're going to talk about into like more methods. So pressure measurement. Sorry, I know my pronunciation is not very good. All right, we have an open end manometer. So this is a laboratory device for measuring pressure. So depending on what kind of work you do in the lab, you may need to measure pressure, or you may need to measure like the pressure of a vacuum that you use. So usually an open end manometer is a good tool for measuring the pressure of, say, you know, maybe your atmosphere or your container that you're using. Okay. So what this is, it's an enclosed. So this is just detailed. I don't expect you to memorize what this is, but if you see it like in a diagram, you should know what it like. You should be able to identify it, but you do not need to memorize like the details of these explanations right here. So enclosed gas pushes one side of a column of mercury. So like what we saw earlier in the barometer example. So the atmosphere pushes on the other side. Again, like what we saw in the barometer. And so it pushes on one side for the mercury, the gas, and then the atmosphere pushes on the other side. Then the difference of the two is what we take as our pressure measurement. So the difference in pressure is measured in millimeters of mercury. All right, guys. So let's talk about another term here, gauge pressure. Again, these terms I probably won't require you to know them for like any quiz or anything. So pressure above atmospheric pressure. So what you read in a gauge is actually pressure above the atmospheric pressure. So that reading is what the like pressure that is greater than the atmospheric pressure. Atmospheric pressure. So these terms will become apparent in a few slides while we're talking about it. So absolute pressure is sum of gauge pressure and atmospheric pressure. All right. So here's a picture of an open-ended manometer. So I'm going to draw it. There's a picture in the slides, so you can refer back to it. So say I have a gas here. So here's my gas, and here's a tube that hooks up to my manometer. All right. All right. So here is my mercury. So here's my pHg. So I'm going to put the level like right here. So for mercury, I'm going to label it gray. All right. So say my mercury is right here. Then my line up here is going to be PA. And what we have here is the equal pressure level. That is balanced by the atmospheric pressure and the pressure of the gas. So for the gas, I'm going to use this yellow color here. So here's the gas mixture. It will enter the tube and will be received by the manometer. And don't you guys miss coloring, like coloring book days, like in preschool or kindergarten? Those were fun. But anyway, can't always color. So anyway, so the pressure of the gas is going to enter this manometer, and it's going to affect the pressure exerted on the mercury. So that pressure difference, when it's balanced out by the pressure of the atmosphere, the mercury will stop moving, and that will tell you the distance that mercury moved will tell you the pressure of the gas that's being exerted. So let's make a few comments about this. So this is PG, pressure of the gas, pressure of the atmosphere is the one on top. And what we can say is Let's say right here. So this is the gas pressure. The yellow part is the gas pressure. And the silver part is the mercury. And on the top here is the atmospheric pressure. What we can say is the total pressure at the same level in the right leg. In the right leg is the pressure. Is the pressure. Is the pressure of the atmosphere. So that's what we call PA plus the pressure difference. Pressure difference, PHG. So thus we have PG equals PHG. Sorry, not PHG. Wrong again. So it's PG of the gas is equal to pressure of the atmosphere plus the pressure of the mercury that moved. Pressure of the mercury. So here we have the mercury, the PHG, that distance that it moved. So say the mercury was at the original level at where PA was, because in our barometer example, we saw that when maybe not the barometer example, but that's where the mercury, pressure of the mercury and the pressure of the atmosphere is the same. They're balanced. They're balanced. They're counteracting they're counterbalancing the other. So now when to measure the pressure of the gas, we have to take the distance of the mercury that moved, so that height difference. So that's PHG that was moved plus the atmospheric pressure that was originally at the same level of the pressure of mercury. So we take the pressure of the atmosphere plus the pressure of the mercury that moved. That will give us our pressure of the gas. Okay, so if we have a closed system, say we have a closed lake. So let's draw another example. Pretty much the kind of same schematic, but we have a closed system now. Okay. So say we have another flask with the same gas, and then there's a tube coming out here. All right, so we have the pressure Hg. So here's the equal pressure level right here, as we've drawn before. Now here is PG. PG is right here. So let's again use our silver to represent the mercury. So the mercury then we use yellow to represent the gas. So in this case, we have a closed leg. So let's see here. So in this case, the total pressure in the closed leg is PG plus PHG. So say say we're the PA, that's where we close the leg. So because it's no longer open to the it's closed off from the atmosphere, right? So well, it's not, I wouldn't say it's closed off, but that's where we that's where it's no longer flowing, or where we kind of push the mercury up to the opposite side. That's what it's talking about. So is PG plus HG, which is equal to the atmospheric pressure. So, and then we can solve for PG would equal PG equals PHG right. So it'd be equal to, sorry, PA minus PHG. So we see here that in the first example, our PG was in addition to the pressure that was moved and the atmospheric pressure, plus PG plus PA. But now in this case, where when our loop is closed right there, in the closed leg right there, where the gas, the length of the gas traveled is now the opposite, in the opposite direction. So now we say that PG plus HG, that level equalizer, will be equal to PA. Whereas the top in the first example, the PA was lined up with the HG. So now it's flipped. PG equals PA plus HG. But in a closed loop, to measure PG, we take the pressure of the mercury and we subtract that from the atmospheric pressure, because the atmospheric pressure is pushing the mercury in the opposite direction. So to solve for PG, we subtract that from HG, because the combination of the PG and the PHG is going to act against the PA. All right, guys. So this example, that's how we measure pressure. Don't worry too much about this diagram. I probably will not ask this kind of pressure question, but we'll go over an active exercise, and this will make I think a lot more sense. So let's move on. Let's just keep track of time here. So we have 20 minutes. Yes, so I was right. It's going to take 2 lectures to cover chapter 4. Okay. All right, so here's our active exercise. So let's practice pressure. So I hope you're doing these active exercises with me. You're pausing the video, maybe work on it yourself, and then we come back and see the solution. And hopefully you guys got the right answer. So in this exercise, the pressure inside a steam boiler. So the application of these pressure is like when if you use like cooking, steamers, steam boilers. I don't know if you guys use pressure cookers, and that applies as well. So pressure, using the pressure of substances has a very important role in everyday life, as you may not have realized. So the pressure inside a steam boiler is 1427 psi. Okay, so let's express this pressure in atmospheres. Okay. So here is our solution. So we're going to say given is 1427 psi, a pressure unit. What we want, what's wanted by the question is a pressure unit, atmosphere. So we know that 1 atm equals 14.70 psi. So you're given that. So we're going to solve for atmospheres, right? We want atmospheres. So we're going to divide both sides by psi. This will cancel out. So what we get, our fraction that we're going to use is 1 atm over 14.70 psi. Okay? So now we take our unit, 1427 psi, put in the fraction we just wrote out, 1 atm over 14.70 psi. We see that the psi's will cancel due to division. And what we're left with is our answer in atm. So 1427 psi, 4 sig figs. So our final answer is going to be 4 sig figs. So 97.07 atm. And we see that makes sense because atm is the smaller unit, psi is the larger quantity unit. So if we divide by the larger quantity unit, we should get a smaller number. And we say, okay, that is correct. ATM is a larger unit psi than psi, and we see that the larger unit, the value or the quantity in front of the unit is smaller. So that's okay. We're good. All right. So hopefully that was okay for everyone. Let's move on to the next one. Okay, let's talk about another pressure conversion. So active exercise. Okay. So the pressure in an automobile tire is 29 psi on a day. the weather. So the weather report states, they're not reports, states that the barometric, states that, sorry, I can't read, that the barometric pressure is 30.09 inches mercury. All right. Our question is, how would you report the absolute pressure in the tire to a colleague in kilopascals, kPa? Okay, so our active exercise, the pressure in an automobile tire is 29 psi on a day. So the weather report states that the barometric pressure is 30.09 inches in mercury. So how would you report the absolute pressure in the tire to a colleague in kilopascals? So what we're given is, so we know that absolute pressure is the combination or the sum of the atmospheric pressure and the gauge pressure. So the pressure that's read like in instrument. So what we're given is 29 psi pressure unit. And also 30.09 inches of mercury, also pressure unit. Also another pressure unit. What we want is, or what's wanted is pressure unit kilopascals. So we want kilopascals, right? So we need to convert both of these measurements to kilopascals. So we know that 14.70 psi equals 1 atmosphere. And we know that 1 atmosphere equals 101.325 kilopascals. So those are the two, that's one of the equations we're going to use. And here's a conversion factor. 29.92 inches equal, not just inches, that wouldn't make sense. Inches of mercury equals 1 atm. And then 1 atm equals 101.325 kilopascals. So the two factors we're going to use is, let's mark this in maybe in blue, 101.325 kilopascals over 14.70 psi, and another one 101.325 kilopascals over 29.92 inches of mercury. Okay, so now that we have our conversion, we can go on here. So let's use our two conversions. So we have 29 psi. So sorry guys, this one might be a little bit long, but it's good practice for converting. So 14.70 psi equals 101.325 kilopascals. So we're going to, so this will cancel out our PSIs and we're left with kilopascals. So notice we have only 2 sig figs for PSI. So our answer should only have 2 sig figs. So you should use scientific notation and get 2.0 times 10 to the second kilopascals. So that is the first one. Now let's use the second one. You just do the second one, 30.09 inches of mercury times 101.325 kilopascals over 29.92 inches mercury. Inches of mercury will cancel out. And what we're left with is 101.9 kilopascals. So notice here, 4 sig figs in our measurement, 30.09. 4 sig figs in our final answer, 101.9 kilopascals. So now that we have all our units in kilopascals, we're going to use the following equation. Pressure absolute equals pressure gauge, so the barometer plus pressure atmosphere. So now that will be equal to 2.0 times 10 to the second kilopascals plus 101.9 kilopascals. And that should give us the answer around 3.0 times 10 to the second kilopascals. So notice when we're doing addition, we only round to the first decimal place because both answers only have 1 decimal place. So our final answer will be 3.0 times 10 to the second kilopascals. So another thing we could check is that our answer, just double check our answer. So we can say 200, sorry, not 200. So to check your answer, you can do the following. Say, so in our first example, we could just round PSI to 30 times 100 over 15. And our answer should be around, 200. Next, our second example with the inches of mercury, 30 times 100 over 30 should give us 100. And once we add those two, 200 plus 100 equals 300. And our answer checks out, so we are okay. All right, guys, so that is one of the active exercises. Hopefully everyone got through that. I know it's a bit long, but these type of calculations are what to expect in general chemistry in Chem 2A. So you'll do these on a frequent basis, and you must be proficient at doing them and very comfortable and know, like, in every step why you did them and to find the answer, to find the value you want. So memorizing will not, I won't say it wouldn't help you, but it wouldn't be the best way to kind of familiarize yourself with these concepts. Okay, let's see how much time we have left. Okay, we have 6 minutes, so I think maybe one more. Okay, so now we're going to move on and talk about so let's talk about, we're going to talk about now the relation of volume and temperature of a gas. So here, volume and temperature. So we're going to be talking about now something called gas laws. So I'm going to just go into like the data part of it. So the relationship is The relationship is like this. The relationship between volume, here's volume and temperature, is a linear relationship, like so. Sorry, that line is very good, like that. So what we say here is that volume is proportional to temperature. So in the slides, they'll talk about as you raise the temperature, the volume will increase. So as you raise the temperature from like 0 to 100, the volume increases from like 60 to 100 millimeters of mercury. So that kind of shows you that once you increase the temperature, the volume of a gas that gets occupied will increase. And that is verified by experiments. So I would take a look at this graph and the figure 4.13. That will give you a good indication of volume and temperature, but they are directly proportional. Okay. Okay, so we talked about absolute zero last chapter. So we're going to, since we're talking about temperature right now, we're going to go briefly over that right now. So absolute zero. All right, what does it mean? So it is, as I said before, the lowest temperature possible at 0K equivalent to a 273.15 degrees Celsius. So at that point, all the molecules do not move, and you can't record a temperature anymore because the temperature is the average kinetic energy of the moving gas molecule. So once they're no longer moving, there's no more temperature, and this is the absolute zero temperature. So degrees Celsius, or a whopping negative 459.67 degrees Fahrenheit. So think about that. You know, we think like 5 degrees is very cold, refrigerator temperature. Think about negative 460 degrees. That is like ice age, not even ice age, even lower than that. So that's when everything freezes. You will freeze. All the atoms, molecules in your body will freeze. And so that is when what we say molecular motion is stopped. And so that means motion is stopped. And at this temperature, we say corresponds to zero gas volume. And so, and then according to kinetic molecular theory, the average, so the temperature, average kinetic energy of the substance is zero at absolute zero. So at that temperature, there's no movement, there's no motion. There's no motion. That's the lowest temperature you can get. And with that, I think at this stage, we will stop here. We only have like half a minute left anyway. So to recap, remember Tuesday, homework 3 is due at 11 p.m. Don't forget to do it. Maybe set a reminder. We will finish chapter 4 on Thursday, and we will pick up on Charles' law, which relates volume and temperature. Right. So volume and temperature, which is what we were just talking about right here. So that is one of the gas laws, and we'll talk more into depth what this relationship means. Anyway, guys, have a great start of the week. Stay safe, and I'll see you on Thursday. All right. Bye.